Chapter 12, Part 2, Nucleophilic Additions to Carbonyls and Grignard Reagents. So the first thing we need to talk about are the physical properties of aldehydes and ketones. Here I've drawn just a ketone, just so we can look at something simple. So one really important feature about the ketone and the aldehyde is that the carbonyl bond is polarized, such that the carbonyl carbon is partially positive, the carbonyl oxygen is partially negative. And don't forget, we have these lone pairs on the oxygen. So this dipole and the fact that we have these lone pairs means that there are going to be some dipole-dipole interactions, and there are going to be higher boiling points for ketones and aldehydes than compounds of similar molecular weights. But that's not the only thing that's so important about this being polar. I'm going to draw another molecule here. Same thing. So this molecule has one really important resonance form. And that resonance form is when we take the pi electrons in the carbonyl bond and push them up onto the oxygen. This gives us a new structure that shows 3 lone pairs on the oxygen and an actual negative charge, and then an actual positive charge on the carbonyl carbon. So these are resonance forms of each other. They're both useful and valid. The one on the left is obviously a bit more stable in the preferred resonance form. It has more covalent bonds. It doesn't have that splitting of charges. But the reason this is so important is that this is the key to the reactivity of all carbonyls, including those that are involved in carboxylic acids and their derivatives. The fact that we have this polarization and that the carbonyl carbon is partially positive and the oxygen is partially negative tells us what will happen when we add in different types of reagents. For example, if I were to add in an acid, say H+, to this molecule, where would you expect the H+ to go? Hopefully what you would expect here is for the oxygen, which is negative or partially negative, however you want to look at it, to interact with the H+. This tells you that there's no reason that the H+ would ever be interested in that carbonyl carbon or vice versa, right? We know that the oxygen is going to have the stronger affinity for H+. What if I were to add in a nucleophile or a base? Something with a lone pair and a negative charge. Where is the nucleophile going to be interested in? Is it going to look at the oxygen, which is either partially negative or fully negative, depending on how you're choosing to look at it? Or is that negative charge going to be more interested in the partially positive carbonyl? Hopefully you're thinking about that carbonyl carbon. The nucleophile is going to attack the carbonyl carbon. And you can also draw that going here. Now, what's interesting about this image that we have going on the left here is that this shows you what happens when a nucleophile attacks a carbonyl carbon, which we are going to look at more on the next slide. So let's look at just a generic nucleophile attacking a carbonyl. The nucleophile is negative, and we already stated on the previous slide that that negative charge is going to be more interested in the partially positive carbonyl carbon than it is in the carbonyl oxygen. So the nucleophile is going to attack the carbonyl carbon. Now, when it does that, we have to remember, and get these charges out of the way, that there are lone pairs on this oxygen already, and this carbon already has 4 bonds. So if we're trying to make another bond through nucleophilic attack, we're going to have to break one, and that's going to be the carbonyl double bond. So this should look very familiar because we saw that same electron movement in drawing out our resonance forms on the previous slide. So what this would give us is our two R groups still attached to that same carbon, our oxygen attached to the same carbon, but now the oxygen has 3 lone pairs and a negative charge. Again, this should look really familiar from the previous slide. And then we have a new bond that we just made to our nucleophile. So let's look at the other changes that have occurred. We pointed out in the previous video that ketones and aldehydes are sp2 hybridized. That makes them trigonal planar and ultimately flat, at least at that carbonyl carbon. So a carbonyl carbon is not a chiral carbon. It does not have 4 things attached to it. Now let's look at our product. Potentially, these R groups could be different. Let's call one R, and then let's go ahead and make the other one R prime. Since this carbon would now have 4 different things attached to it, we've done a few things. We took our sp2 carbon and we turned it into an sp3 carbon. Our trigonal planar carbon has become tetrahedral. So let's go ahead and give it some 3D shape here. Let's make this a wedge and make this a dashed line. And that also means that we could now have a chiral carbon and possibly a chiral compound. It just depends on the identities of these R groups and the identity of the nucleophile. So if we start off with something flat and we end up with something with 3D shape, remember there's not going to be a preference for which side the nucleophile comes from. So you're likely to end up with a 50-50 racemic mixture here. Oops. Of your 2 different enantiomers, diastereomers, whatever the situation is. Just depends on your starting material. So a couple important implications about this. So let's introduce a new type of nucleophile. We are now looking at our Grignard reagents. Grignard reagents are organometallic compounds that have a highly polarized bond, and they have the format R-MgBr. So this is really interesting. This isn't something we've seen before because we actually have a covalent bond between a carbon and a metal. And even more interestingly, the metal is actually inserted in between the carbon and a halogen. So everything about this is really new and different. And this is highly polarized, maybe not in the way that you think. The magnesium is going to be very, very positive, even though I know bromine is electronegative. The magnesium is going to be very, very positive, and the R group, very, very negative on the carbon directly attached to it. So let's look at the example below. This carbon is the carbon directly attached to the magnesium. Let's go ahead and just highlight it as carbon, and it does have 2 hydrogens on it. Let's go ahead and give it that. This bond is highly polarized. There's a huge partial negative on this carbon and a huge partial positive on magnesium. So when we look at a Grignard reagent and we consider its reactivity, we're going to look at it like it is a carbanion, but it is not a carbanion. It is actually a covalent bond that is highly, highly polarized and unstable. And so it does behave like a carbanion, but it is not a carbanion. So let's look at what that means on the next slide. Well, first we have to look at how we form them. So on this slide, we're looking at the synthesis of the Grignard reagents, and then we'll talk a little bit more about how it reacts. So a Grignard reagent is synthesized by taking an alkyl halide, bromine, chlorine, or iodine typically, and reacting with magnesium metal. That's what the little 0 means. It means that it has a charge of 0 and therefore is not magnesium ion. but actual magnesium metal, and it's going to react in ether. Now here I've just gone with the word ether. When you're working on Achieve or you're looking at an exam, but especially on Achieve, they tend to get really creative, and Achieve likes to use several different ethers. I'm going to go ahead and just draw out a list here. So THF is one of them. We've seen THF a few times before. That's tetrahydrofuran. They also like to use glyme and diglyme. They may also write out like dimethyl ether or something like methyl or ethyl ether. Anything that is an ether that's indicating that it's an ether is going to just be the solvent here. It has nothing to do with what ends up being the product. It's just the solvent in the reaction. And if you're looking at something like this and you see an alkyl halide and magnesium, don't get tripped up on whatever that extra thing is. If you Google it and you see that it's an oxygen with carbons on the ether side, then you know that it's an ether and it's just the solvent in the reaction. So I just wanted to have a little side discussion about that. I'm gonna just continue on here. So what happens here is that the magnesium does end up kind of inserting itself. It's not really a mechanism. I don't mean to imply that, so I'm not going to draw out an arrow again. But it inserts itself in between the carbon and the bromine. And so the only thing that you're changing is that you're writing in magnesium bromide instead of just bromine here. And you can also do this on an sp2 hybridized carbon, and you can also do it on an aromatic carbon. So here we have chlorobenzene. In here we have a magnesium chloride. So both of these are examples of Grignard reagents, and they would both behave as a Grignard reagent. This one was the one from the previous slide, so I just want to reiterate here that with this benzene, what that would mean is that the way that we would interpret the reactivity of this molecule is like it has a lone pair and a negative charge on that carbon. Even though that's not really what's happening, that's how it's going to behave. Okay, so let's look at the reaction of Grignard reagents with protic acids. This is our first kind of introduction to how Grignard reagents behave. So Grignard reagents are good nucleophiles, and they are also strong bases. The pKa of an alkane is 50. And if we are kind of treating these Grignard reagents like they are carbanions, then they are essentially the conjugate base of an alkane. So this is equivalent to you somehow pulled a proton off of an alkane, even though it has a pKa of 50, and now you have the resulting base of that. So this is a very, very strong base. It is going to react quickly and probably violently with any source of protons. So for example, if you have ethyl magnesium bromide and you mix it with water, which would not be a super smart idea, what's going to happen is that the carbon here, which is the one that's acting like a base, is going to attack the water and pick up one of those protons. So the way that that looks, if we were to draw a mechanism, is the electrons in this bond between the carbon and the magnesium are actually the electrons that are doing the chemistry. So those electrons would attack that proton, and we give these electrons back to the oxygen. And that's how we end up with a CH3 here. We add a proton to the carbon. We have hydroxide, which is the conjugate base of water. So let's go ahead and give these some labels here. Base, acid, conjugate acid, conjugate base, side stuff. Just counterions, essentially. Notice that the three of these together end up as neutral. So this is a side reaction that you have to be really, really cautious about anytime you're using Grignard reagents. You don't want to use alcohols as your solvent. You don't want to be trying to react with a ketone on a molecule that also has an alcohol somewhere else on the molecule. Groups that this includes would be water, alcohols, acids, amines, thiols, anything that's going to have that extra hydrogen that's able to act as a proton. Let's take a look at how these Grignards actually add to carbonyls. So typically this is a multi-step process. Here we have a step 1, step 2 kind of situation. Oh, that's weird. Step 1, step 2. And what happens is your Grignard is going to act as a nucleophile, and we discussed how nucleophiles attack the carbonyl carbon. I'm going to go ahead and mark the carbonyl carbon with a blue dot just so we can track it. So these electrons are going to attack here, pushing the pi electrons up onto the oxygen. So our blue carbonyl carbon is right here. And then we have 2 carbons from our Grignard appearing in the product. So we have 3 carbons involved in our reagents, which means there should be 3 carbons in our product. Now notice this product is charged. So typically, this type of reaction is followed up with what's called an aqueous acid workup. Now the aqueous acid workup does 2 things. It neutralizes your product, but it also gives you a chance to slowly neutralize your Grignard with some control, because you don't want to have unneutralized Grignard around. As we mentioned, it's a very strong base. If you accidentally expose it to too much water and you happen to have a lot of Grignard left, you could actually have quite a dangerous reaction on your hands. So typically you would do a slow and controlled aqueous acid workup. Now the way that this problem would actually be given to you on a quiz or an exam would typically be something more like, we have an aldehyde, and then in step 1, it's exposed to a Grignard. And then in step 2, you have some sort of conditions that indicate acid and water. And you're supposed to come up with your final product. But there's another kind of more interesting way that you can see Grignard problems as well, and that involves starting with an alkyl halide. So in step 1, you would add in magnesium in whatever ether. In step 2, you would add in a ketone or an aldehyde. And then in step 3, some sort of conditions that indicate acid and water. Right, we've seen this before, that there are a lot of different ways to indicate acid and water. I could give you H plus and H2O like I did up here. I could give you H3O plus. I could give you H2O and sulfuric acid. I could give you 0.1 molar sulfuric acid, right? Anything that indicates that there is a proton source. And in this one, we're actually starting by generating our Grignard. So our product in step 1, if you want to go ahead and pause and work this out yourself, I think that's a great idea. And if you don't want to do that, I'm going to keep working. So in step 1, we are inserting the magnesium to make our Grignard. In step 2, we are introducing our ketone. And I want to take a second and really draw attention to how these products are drawn, because a lot of students start to lose or gain carbons because they lose track of what they're doing. So let's think about what this is actually doing. These electrons right here in this bond between carbon and magnesium are the ones attacking at the carbonyl carbon. So one really good way to draw your intermediate here would be to start with the carbon framework of your ketone. And now we know that we just created a single bond with a negatively charged oxygen. We also know that we just created a bond to our Grignard. And our Grignard has 1, 2, 3 carbons. So far, all I've drawn is everything that was part of my ketone. And now I'm going to add on my 1, 2, 3 carbons from my Grignard. So this is my intermediate. Now the next step that's not a bad idea to take is just to double check that all the carbons that you meant to draw are there. So we've already labeled these 1, 2, and 3 on our other example. Let's give these other ones a label as well. 4, 5, 6, and 7. So that'd be 4, 5, 6, and 7. No, this is not correct nomenclature numbering. That's not what we're doing. I'm just numbering them to help us keep track and make sure that everything that was supposed to end up in the product does end up in the product. And then we're going to do our aqueous acid workup. So we protonate our alcohol. And that's our product. So you know I love to summarize our reactions in a table. Here's your summary for your Grignard addition. So if you are starting with formaldehyde, remember formaldehyde is just one specific aldehyde. It has 2 hydrogens attached to the carbonyl. So that's formaldehyde. It's also drawn here. So formaldehyde, when reacted with a Grignard, will always make a primary alcohol. And make sure that when you're looking at this chart that you're kind of keeping track of what you're seeing. Here's our carbonyl carbon, and here it is in the product. Our Grignard I marked as R prime so that you can keep track of it in the products. Notice that for all of these I used the exact same reaction conditions just so you can keep track of it more easily. For any other aldehyde, reacting with a Grignard is going to make a secondary alcohol because that other R group is going to be there as well. So here's our carbonyl carbon. And we have our R group from our original aldehyde, and we have our R prime from our Grignard. So secondary alcohol is our product. For a ketone, the ketone already has 2 of its own R groups. Let's keep track of that carbonyl carbon. It's right here. Here are the ketones R groups. And then we have the R group from the Grignard right here. So we always end up making a tertiary alcohol. Now I do want to show there's a difference between reaction of a ketone and an ester. And we haven't looked at how esters react yet. That's coming up in a later chapter. But we will see that soon, and you'll see that you end up making a tertiary alcohol as well. But it does it kind of differently. So I just wanted to point this out in this table. We don't necessarily need to know how this happens yet. I just wanted to have the information together. So the carbonyl carbon, we're keeping track with the orange. Notice that the R group that's directly attached to the carbonyl does make it into the product, but the Grignard actually ends up adding twice. So we end up with 2 equivalents of the Grignard. And so that's actually different from what happens with the ketone. And when we get into chapter 14, when we actually talk about reactions of carboxylic acid derivatives, we'll explain how that happens. But for now, I just wanted you to have all the information in one place.